Okay. Speed, velocity, and acceleration. Speed and velocity are giving us an idea of how fast an object is moving, isn't it? So probably our most common interaction with speed is in our cars. Okay, so the car tells us our speed, doesn't it? Mm-hmm. Why is it that the car isn't giving us our velocity?
Is velocity like the average or no? No. It's because we don't really need the direction.
Yeah. So our speed, again, just like we had our distance and displacement, as the distance being scalar and the displacement being a vector, speed is a scalar quantity, and velocity is a vector quantity. And so that means that to find the velocity, we are going to need direction. Whereas the speedo in your car is just telling you how fast you're going at that time. Now, there are instances, certainly, where they're the same, but they're not necessarily the same. And they can be very, very different. And so our units, our SI units, and we use SI units for our communication in science anyway, but it's particularly important in our physics component. SI stands for Système International, which is basically the metric system on a sort of small level, but then it goes on and it tells us what is the systematic unit that should be used around the globe when you're conducting a scientific experiment. And if you get this wrong, then, or if different groups are using different units of measurements, then problems are going to happen. One significant problem with this was crashing a rocket or an exploratory vehicle onto the surface of Mars. That's one where they got the measurements wrong. Okay, one lot were using imperial measurements and the other lot were using metric measurements, and so when they were trying to calculate the descent velocity for this thing, they got it wrong and it crashed onto the surface. The same with the grinding of the Hubble telescope, got that wrong. And so these sorts of things are important, that you need to make sure your units are right. So the SI units for our speed and velocity is both meters per second. Okay, meters per second. So meters per second means that you've got your meters and you divide it by the seconds. That's what the power of -1 means. However, this one is meters per second plus direction. But when you're doing your calculations, then you would be calculating your meters per second. Another common one we'll see is kilometers an hour. Okay, so that's kilometers per hour. And this is what we often talk about when we're looking at vehicles. So sometimes you might have a question that's in kilometers an hour and you have to convert it to meters a second, Or it could be the other way around, where you're given it in meters per second and you need to convert to kilometers an hour. We just use, I don't have to explain the maths of it, but we just use a conversion factor of 3.6. So if you're going, it's on your on page 11 here, if we're going from meters a second to kilometers an hour, then we have to multiply by 3.6. And if we're going in the opposite direction, then we divide by 3.6. Now, if you remember the 3.6 and then you can't remember whether it's multiply or divide, you can apply logic to it. You can try it and see, does this make sense? If I'm travelling at 60 kilometres an hour, what would that look like if I accidentally multiplied by 3.6 to get to the meters per second? What would that be telling me I'm going? What's
120 meters. 180.
Like over 200.
180, 100. What's it actually? Has anyone got a calculator? So let's look at what would happen comparing the two.
That's 260. Oh, it's just a bit.
260.
16.
216
Oh.
meters a second. What happens if we divide it by 3.6?
16.6 recurring.
So just say we're asked to convert between them and you accidentally multiplied. Hopefully you would look at that and think, when I'm driving in the car at 60 kilometres an hour, am I going to be able to go a kilometre in 5 seconds? You know, like, that's really, really fast, isn't it? That would mean I could get to Launceston in 500 seconds, or from where I live, which is very, very rapid. It doesn't make sense. And so you can just do the double check and make sure that the meters per second should always be less than the kilometres an hour. But the reason why this is our conversion factor is we've got 1,000 meters in a kilometre, and in an hour we've got 60 times 60 to minutes and seconds. So this gives me 1,000 divided by 3,600 in that instance.
Does that have to be the other way around?
Well, it depends on which way, yeah. That's why this one would be making it smaller, putting it around that way. We're going for meters per second. All right. So our speed is equal to the distance we travel divided by the time. Okay, so remember that we've already talked about distance being a scalar and our speed being scalar. Time is also scalar. But our velocity is equal to displacement divided by time. So this is a vector and this is a vector. And we often will see this represented as a formula: V is equal to S over T. It could also be V is equal to delta S over delta T. Do you know what the delta means?
The difference.
The difference, yeah. The change in or difference. Yeah. And so we tend to just use this formula using the words, because if we end up putting in these letters, we'll end up confusing ourselves, because if S is speed and then S is displacement, and then if we've got D in there for distance, and we could also mix up distance with displacement. So it's safer to just leave that one as words, and to use this one, you can use this one as in this formula arrangement. And of course we can also rearrange this to find other factors. So what's time going to equal for our speed?
Distance divided by speed.
Yeah, distance divided by speed. And obviously then our distance is equal to the speed times time. Our calculations won't work unless our units are consistent. So if I've got a distance in kilometres and a speed in kilometres an hour, and I'm working out time in seconds, then I've got some conversions that I need to do, okay? So the units must match within the context of the question. Okay, and we'll have one last little chat about acceleration. So when you're driving or in your car, depending on whether you're the driver or a passenger, if you're on the highway and you're cruising along 100 kilometres an hour, 110 kilometres an hour, you generally got your foot pretty steady. You don't, unless you're going up and down hills, you know, you can sort of sit there with your foot pretty still, and the car just sort of maintains that velocity quite, you know, without too much extra effort. That's quite different to if you're, say, stopped at a set of lights and you want to get going quite quickly, don't you? You have to put your foot down on the accelerator to get yourself moving more quickly, and that is acceleration. So velocity is moving with a constant speed in a certain direction. Okay, that's what velocity is. If it's constant velocity. But if you can have changing velocity, if you're accelerating, so accelerating this is the rate of change of velocity. So if you think, you know, you're stopped at a set of lights, if you're stopped at the lights, you're going 0 meters a second, aren't you? And then the lights turn green, and after 1 second, you might be going, say, 5 meters a second. And then after 2 seconds, if you had constant velocity, you would still be going 5 meters a second. But you probably aren't. You might be up at 10 meters a second. Okay, because you're accelerating. And then at 3 seconds, you're up at 15 meters a second. And we've already worked out that 60 kilometres an hour is around about 15.7 metres a second. So, you know, by about, let's say, 4 seconds, you're at 20 metres a second. Well, hopefully you're not in a 60 zone because you're speeding now. But see how this is our velocity. This is time. And because this is increasing, this is telling me I'm accelerating. Because my velocity is increasing. And that's why acceleration then is the rate of change of velocity, which is also a vector quantity. And if we took this example here, we would say that our acceleration in this example, we accelerated from 0 to 20 over 4 seconds, gives me an acceleration of 5 meters per second squared. Okay, because it's the rate of change of velocity, it's meters per second. And we write that as meters per second squared. This is also a vector, and so we need direction. At the moment, what we've been considering has been averages. Okay, so I averaged out the acceleration here, and this would be an average velocity as well. We can also calculate instantaneous velocities, but we're going to stick with average for the moment. Okay, now we've got a worked example on page 12. Let's have a quick look at that. A netballer doing a warm-up drill jogs up the 30-metre netball court in 8 seconds. Now, the way to do these questions is to write out, I like on the left-hand side, write out all of the things that you know. Okay, so we've got time is equal to 8 seconds. And in that time, she's gone 30 metres. So we're going to call our displacement, we can call it S if you like, but it can also be X. Okay, so S or X doesn't really matter. Then, so this is, if you like, event 1. Event 2 goes for 3 seconds, where she's waiting. So she's waiting. So that means our displacement is 0 meters. And then she sprints halfway back, taking only 3 seconds. So event 3, T is still 3 seconds, but she's gone halfway. So that's going to be 15. But if we're thinking about displacement, it's negative. If I have decided that this way is positive with my 30 meters, then when she comes back this way, halfway, then that must be minus 15 for displacement. Now we're asked, well, if we use all this information to find out her distance, remember it's scalar, and so we just want the absolute value. Are you familiar with this? Are you familiar with those lines? No. Okay. So these straight lines on the outside of something mean it's the absolute value. It means that you don't worry about whether it's positive or negative. You're just taking the positive part of it. Okay, so that's the magnitude, or absolute value. Or do we do that in maths? And so for our distance, then that is going to equal 45 meters. Positive, isn't it? Because we're only interested in the magnitude, not the direction. Time is going to equal 8 plus 3 plus 3 is 14 seconds. So the speed, which is distance over time, will equal 45 divided by 14, 3.21 meters a second. Now for our velocity, which is a vector, this time we have displacement. And we are interested in direction. So that is going to equal 30 plus 0 minus 15 is going to give me a displacement of 15 metres. Time is still the same. So when I work out the velocity, being the change in displacement over time, I will get 15 divided by 14, 1.07 metres per second in the positive direction. And we write that if we're not given a direction in a question. Okay, so we weren't told that up the court was positive, but we are assigning that as positive. So within our coordinate system,